Okay, so what we want to do now is talk about how do we analyze the forces in a force pair. How do we do it? How do we work it? Oh gosh, this is a lot, but let's talk about it. So this is Tactics Box 8.1. I don't know if it's from the old book. Okay, identifying action-reaction pairs. So this is a great method that will help you analyze these kinds of situations. First thing, draw each object separately. Place them in the correct position relative to other objects. Don't forget to include objects like the Earth that may not be mentioned in the problem. And so typically, even if something is touching, we're going to draw them separately. And you'll see why as we do an example. So draw every object separately. Number two, identify every force. And so this is nice. Up until this point, we've been using like the normal force and weight and things like that. I mean, you can do that, but it makes life a little more difficult. It's better to use this kind of notation. Like if it's weight, you're going to say the force Earth on, whatever, book or something like that, If you do, you'll see why this is actually much better than using normal and weight when you have this kind of a problem. Okay, so identify every force. Identify action-reaction pairs. Well, if there's an Earth on book, there has to be a book on Earth, right? So there should be no unpaired forces. Now, Randy Knight likes this. He says, connect the two force vectors with a dotted line. That's not a good idea, I guess. When you're done, there should be no unpaired forces. Okay, that makes good sense. Identify the objects that are systems of interest. Like that one that we had over here with the table and, me pulling on the table. We didn't care about me, we cared about the table, all right? So you want to identify the objects that are systems of interest, and then draw the force diagram for the system of interest. Now look, this is important. Include only the forces acting on the system, not forces that the system exerts on other things. Come on, it's a force diagram. You only draw the forces acting on the object, right? I don't care about the other things. So there's nothing new here, It's same old, same old. All right, so let's do an example. So here, we have a box sitting at rest on the floor. And this is how I'm going to draw it, like it's levitating, right? All right, because you want to draw the objects separately. So we have a box. We have the surface of the floor, and we have the Earth. So you got to include everything, Got to include everything. Okay, so 3 objects. My gosh, right? 3 objects, yeah. All right, so I guess we don't usually, we haven't worried about the Earth before, but now we got to start worrying about the Earth. So it's obvious you're going to draw the box and the floor, but now you got to draw the Earth as well. Okay, now, how many forces act on the box? Well, you know that. There's the normal and there's the weight. Oh, now let's not do that, right? What's the normal? So the normal, that's a force surface on box, right? And what's the weight? It's the force Earth on box. And notice, I just said there's 2 forces on the box. Look. Surface on box, Earth on box, right? So the box is the object. Okay, so, there you go, right? All right, now, whatever. You can use whatever notation you want. You can put an N here, or an F here, or whatever. But the important thing is, in my opinion, surface on box, Earth on box. That's the important thing. Okay, now, every force is a member of a force pair, right? So if there's a force surface on box, there has to be a force box on surface, right? If there's a gravitational force Earth on box, it has to be a gravitational force box on Earth, right? So the next step is what we're doing here, right? So now we're just doing the action-reaction pairs, okay? Come on. All right, so now we're doing, okay, so We drew each object separately. We identified the forces. Now we're identifying the action-reaction pairs. Okay, so surface on box, box on surface. Earth on box, box on earth. Right? All right, so it's not so bad. Equal and opposite, right? So same magnitude, opposite direction. Same magnitude, opposite direction. Now, what do we care about? What's the object of interest? It's a box, right? The box. So there, right? Okay, so we identify the objects that are systems of interest. The box, all right? The box. Okay? Now, and then what do? What's the next step? You draw the free body diagram for the box. Okay. Now, if you've been following along, you should be thinking in your head, what a total waste of time. I mean, I could have done this in 2 seconds, just using what we learned last chapter, right? Well, I agree. Total waste of time, all right? But I did it for a reason, just to show you the process, right? Because now we're going to add another box, and then you'll understand why we do this, okay? So now what we're going to do is we're going to have another box, okay? So we have 2 boxes, right? One box on top of the other box, okay? And now what we want to do, okay, so here we go. Draw each object separately. Box, box, floor, earth. Identify every force. Okay, now think about it. What are the forces on box B? Well, you know, there's gravity, there's the normal from the floor, but wait a minute. Isn't this guy pushing down, right? Isn't this guy pushing down? Yeah. So we have a normal box C on box B. So now there are 3 forces acting on box B, right? 1, 2, 3, okay? What are the forces acting on box C? Well, you know, there's always gravity, right? So there's the weight, Earth on C, but isn't this pushing up? Isn't this a normal force? Yeah. So the normal force B on C, okay? All right? So there's 2 forces acting on box C, gravity and the normal from this one. There are 3 forces acting on B, gravity, normal from the floor, normal from box C, right? All right? And then we got to match, then we got to get the reaction pairs, all right? So B on C, C on B, got it. Earth on C, but there better be a C on Earth, right? Remember? This is pulling up on the Earth, right there. Okay, we already have S on B, B on S, and we have these 2. So there you go. Kind of more complicated, right? Complicated. So this, I know, this helps, I think, if you follow this tactics box, you know? Get all these different forces. Now, what do we care about? Well, we probably care about the boxes, right? Care about the boxes. So now we're going to draw the force diagram for both boxes. Okay, so for C, I mean, it's kind of no kidding, right? For C, you know, we have the gravity and we have the normal B on C. That's sort of obvious, right? But the one that maybe you didn't think of, which I've already been talking about, is this one. So there's normal floor or surface on B, but now there's 2 down forces, right? There's the gravity, Earth on B, and this guy is pushing down on it. So there's normal C on B. So this, I guess, is the new part, right? This is the new part, or the new thing that we're supposed to be learning, okay? There are 2 normal forces acting on box B. All right, so that's kind of like the big deal. Okay? All right, we'll use that, don't worry. All right, here's a question for you. Your hands push on a heavy box to slide it across the floor. What's the other member of the force pair? So pause your video and figure it out. Okay, let's do it. So there's a force, U on box. So what's the other member of the force pair? The force, box on U. and they are equal and opposite. All right? U on box, box on U. A on B, B on A. If you just remember that, you won't get confused. All right. Oh, this is a good one. Mary pushes horizontally on a large, heavy table, which is standing alone in the middle of a room. It notes that the table does not move, despite the fact that she is pushing on it. Why doesn't the table move? Okay, hint, what's the object? And then the table, obviously, right? So draw the force diagram. So please draw the force diagram and then answer the question. And you have to be, all right, so draw the force diagram, answer the question. So pause your video and figure this one out. Where's the trash can? All right, I assume you've done it. Okay, so the object is the table. All right, so there's, the normal force, which we don't really care about, and there's the weight, which we don't really care about. So here we have the force of Mary, right? Now, how come the dumb table's not moving? Because there's friction, right? So there's some friction, Fs, right? And that's all. Right? It doesn't move because there's friction opposing, and her force, so the force of Mary does not exceed Fs max, right? So the table doesn't move because force of Mary is not greater than Fs max. Well, that was stupid. Force of Mary is less than Fs max. How's that? Yeah. Okay, that's why, So what's the answer? There you go. Okay. All right. Yeah, this is the same thing saying the F force of Mary is equal to just the Fs, right? Which is less than Fs max. Okay. Now, this is kind of a cool one because, look, let's just go through it. Okay, a frictional force is also exerted by the floor on the table, and this force is equal and opposite to the pushing force. Perfectly correct. The table exerts a force on Mary, and this force is equal and opposite to the pushing force. Now, this is a correct statement, right? Number 2 is right. Number 2 basically says the force Mary on table equals the force table on Mary. Equal and opposite. Now, that's a totally true statement, right? But does it answer the question? Does it answer the question why doesn't the table move? Not at all. Because here, Mary's the object. We don't care about Mary. We care about the table. So this is kind of a tricky question because this is a true statement, but it doesn't answer the question. So you got to watch out for things like that, right? That's why whenever you have a multiple choice test, you want to always read every single answer. Okay. 3, the force of gravity pulls downward on a table, and this force cancels the pushing force. That's the most ridiculous thing I've ever seen in my life. Not really, but how can a force this way cancel a force this way? It can't, right? It's, right? How can it? They're perpendicular. How can they cancel? Okay, 4. The table pushes back on Mary with a force that's even larger than Mary's pushing force. Well, that disagrees with Newton's third law, right? Newton's third law says Mary on table equals table on Mary, magnitudes, Okay, so I love this question. Love this question. All right, now, you may be wondering, this is all this wonderful Newton's third law. What good is it? Why do we care? So now we're going to talk about something called a propulsion force. Okay, propulsion force. All right. Way back when, not really, but we said that F equals ma. What it really means is the sum of the external forces equals ma. Right? That's what it really means. Right? Now, so in other words, the only force that causes something to accelerate is an external force, right? Okay, so if we were in class right now, I would come up to a student, and I would already talk to the student, and I would pretend to grab the student's nose, and I would yank it. And, well, if I really did that, which I wouldn't, but if I really did that, would I accelerate the student? Of course I would, right? You know, I would have the student pick up their feet, you know, so they're just on this nice chair with nice wheels, and I would pretend to grab the student's nose, and I would, right? So this, I could easily accelerate a student by pulling on his or her nose, right? Because that would be an external force. Okay, then what I would do, maybe I'll do it. So here, you're in your house or wherever you are. Okay, so sit in a chair and pick up your feet, and hopefully you have a chair with rollers, I don't know, and grab your nose and please accelerate yourself. Okay? Grab your nose and accelerate yourself. Well, are you able to do it? No, you're not. Why not? Because when you're grabbing your own nose, that's not an external force, right? If I were to grab your nose, that would be external force. I could accelerate you. But when you're pulling your own nose, that's not an external force, so you can't accelerate yourself. Okay? So that's a big deal, you know, external force, external force. I don't want to see that. Go away. Yeah, all right? So you can't get anywhere by pulling on your nose, as you just demonstrated. All right. So what we want to talk about now is something that we do every day. Let's walk. We want to talk about walking. Why do we want to talk about walking? Because you need Newton's third law to explain it. All right? So let's say it's beautiful outside, summer day in Hawaii. And let's say we're at Hukilau Beach. So I'm standing on the sand, the water's over there. I'm sitting at rest, I want to go swim. So, let's see, I'm the object. I want to accelerate, right? In order for me to accelerate, there has to be an external force acting on me, right? I mean, I'm the object, you know? So here's the question. What is the external force that acts on me, which allows me to accelerate and go in the water? What is it? So think about that for a minute. Remember, it has to be external. I'm the object. Now I chose the beach for a good reason. You know, again, if that's the water and you're standing still, what do you got to do? I mean, if you do this, you're just going to go up. That's kind of silly, right? What are you going to do to the sand if you want to go that way? You got to what? You got to push back, right? You got to push back on the sand, right? So you have the force U on sand, and that's that way, right? Well, Newton says there's forces come in pairs. What's the other member of the force pair? The force sand on U. Magnitudes are equal, but what's the direction? That way. So that's what it is, okay? You push on the sand, whoosh, sand pushes on you, and you get to go wet, get wet, okay? So let's draw the force diagram. So remember, you are the object. What are the forces acting on you? The normal, the weight, and now you have this force sand on you. We don't draw you on sand because we don't care about the sand. The sand is not the object. You're the object. Sand on you. So we give this a name. This is called a propulsion force. So the force sand on you is a propulsion force. Okay? Propulsion force. Okay, another example, think of a bicycle. Think of a bicycle. What's the external force that causes a bicycle to accelerate? Remember, you're part of the bicycle, so it's not you, right? You're part of that bicycle. So what's the external force that causes a bicycle to accelerate? By the way, I mean, you're part of the bicycle. You don't believe me? Think of it like this. Let's say we had a bicycle right here with a rider, and let's say we could somehow tie it to the, I don't know, tie it to the ceiling somehow, right? So the bicycle is right here. It's not touching the floor. So let's say that the person is riding the bicycle, pedaling as fast as he or she could. Well, is the bicycle going to go anywhere? No, right? Because you need a surface, right? Okay, so I just gave it away. So what's the external force? Well, for a bicycle, you have the force of the tire on the road, right? And then the other member of the force pair is the road on the tire. And they're equal and opposite, right? Think of the bicycle, right? The force of tire on road is that way. The force of road on tire is that way. All right? So there you go. You cannot explain walking. You cannot explain how cars, the car or bicycle without using Newton's third law. I mean, kind of cool, right? So, go away. So, yeah, so this is the force diagram. I included everything I could possibly think of. This is like the car and the bicycle. So you have the normal and the weight, no kidding. You have the road on the tire, or wheel, whatever, But then you also have the rolling friction, and you also have air resistance. Now again, usually we ignore these two, but I just wanted to put everything on it, everything. Okay? How about this? Let's say you have a rocket in deep outer space. So again, there's nothing out there, right? That's the assumption. Nothing out there, okay? But, you want your rocket to go faster or slower or take a left or a right or up or down or who knows. You want your rocket to accelerate. How do you do that? There's nothing to push against, right? I mean, it's a perfect vacuum, pretty close. How do you do that? Well, think of a rocket engine, okay? Think of a rocket engine. Hold on. No. Okay. Go away. All right. Think of a rocket engine. So here's my super duper rocket. All right. Here's a rocket engine. What does a rocket engine do? A rocket engine pushes out high pressure air, let's say, all right? Okay, so there's a force rocket on, let me say gas, all right? So the rocket engine pushes out like high pressure gases. So there's a force rocket on gases, right, from the engine. Because remember, this is a vacuum. Well, Newton's third law. So there's also, all right, and that's this direction, agree? That's the force rocket on gas. So there's equal and opposite gas on rocket, which is going to be that way. That's how it works. So you can accelerate rockets in the middle of deep outer space. Piece of cake, just Newton's third law. So here's a funny one. Okay, so I don't care about the practicality of this, but how about the physics? Is this possible? Would it work in our imaginary world? So what are these guys doing? They have a whole bunch of shoes and boots, and they're throwing them out. Is it going to accelerate the rocket? You betcha it would. Why? Well, because the shoes are taking place of the high-pressure steam or whatever. Gas is coming out of the engine. So in other words, we have force rocket on shoes. Let's just say shoes, right? Right? And that's this way. What's the other member of the force pair? Force shoes on rocket. And that's that way. It would work. I mean, it would work. I mean, it wouldn't work all that great. The acceleration would be pretty small, right? But, I mean, the principle The principle is correct. Here's another one. So in the United States, when they shoot up rockets, like one place they use is a place in Florida, I think it's Florida, Cape Canaveral. So they have the ground, and they have this big giant rocket. And then they have the astronauts are up here somewhere, so they have like an elevator. So they go up here, and they have to have these things holding the rocket so it doesn't fall, right? Okay. Now most people think that you need the ground underneath the rocket to accelerate it. You don't. I mean, you need the ground so the rocket doesn't, to keep the rocket in place, right? But what I'm saying is, if somehow you could hold up the rocket, like on the side or something, and if you could dig a big hole underneath the rocket, so here's the rocket, so dig this big hole, would the rocket launch? Of course it would, because it's a rocket engine, right? You have rocket engines, So again, you have the force rocket on gases, and that's equal and opposite to the force gases in the engine on rocket. All right, so you could launch a rocket if you had a big giant hole underneath it, as long as you could hold up the rocket so it wouldn't fall, Now, this is kind of fun. This is kind of a nice historical story behind this. Okay, this is Robert Goddard. He's like the father of modern rocketry. So he understood Newton's third law, and he figured out how to build a rocket. And, I mean, he's the guy. Figured out how to work rockets, right? All right, let's see. Okay, it says he was born 1882. Let's see. By 1926, he had designed and built and flown the first rocket. Okay? Now, let's see. Okay, now, so he understood. I mean, he succeeded, right? He built a rocket and it worked. But here's what's funny about it. So all right. So this is from the New York Times, one of the best newspapers in the world, right? And this is what they wrote, 1920. So this is before Goddard had shown that this thing would work, right? Okay. So this is New York Times. New York Times says, Professor Goddard, with his chair, like he used like a physics chair or something like that, and in Clark College, and the countenancing he was supported by the Smithsonian Institution, does not know the relation of action to reaction and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. So what's the New York Times saying? They don't understand Newton's third law. They're saying that you need a solid ground here to launch a rocket. You couldn't just have a hole here, right? So New York Times is poking fun at Goddard. They're saying, man, this guy doesn't even understand high school physics. This whole rocket thing is a bunch of baloney, Well, obviously, Goddard was right. New York Times was wrong, And so look at this is 1920, right? So finally the New York Times in 1969, 49 years later, a correction. All right. On January 13th, 1920, New York Times dismissed the notion that a rocket could function in a vacuum, blah, 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 blah. Further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well as in an atmosphere. The Times regrets the error. Yeah! So it's pretty funny, right? I think it's pretty funny. All right. Couple questions and then we'll quit. You are standing still on the floor. Which of the following statements must be true? Must be true. So pause your video and figure it out. All right, let's do it. Okay, which of the four statements must be true? Well, if you're standing still, so relative to the Earth, your acceleration is 0. Okay, right? Okay, so 1 is true, 2 is false, right? Gravity is pulling down on you, the normal force is pushing up on you. Okay, so 2 is false, 3 is true, right? If the acceleration is 0, the net force is 0. Okay, now 4. The normal and gravitational forces exerted on you cancel. Correct! They're equal and opposite. All right, so 1, 3, and 4 are correct. Okay, great. Now, this is like an add-on. You're standing still on the floor. Which of the following statements is always false? Which is always false? So pause your video, figure it out. Okay, so 2 is false. We already talked about that. How about this? The normal and gravitational forces exerted on you are the same, are members of the same force pair. That's false, right? Because what's the object of the normal force? You. What's the object of the gravitational force? You. Members of the force pair can't have the same object. So 2 and 5 are false, always false, okay? So I'm just trying to, emphasize this. Just because two forces are equal and opposite does not mean they're members of the same force pair. So don't get confused on that. All right, let's quit.